Hey, so I'm going to be showing you my CloneCraft Minecraft clone program. It's very long currently. It's just about 1,700 lines, and all it does is hopefully this doesn't crash my OBS. It renders a nice colored triangle. That's it. That's all it does. It took me all week. You can change the size of the window, which is kind of nice. That was a bit tricky to handle. You can minimize it and it doesn't freak out. It would be printing a bunch of errors here if that was the case. But yeah, and then you can close it and then it waits for you to press continue and hooray! Code 0. There's no memory leaks, which is fantastic. There is currently no interaction. Literally all it does is render a triangle. And that's because in Vulkan, there is a huge amount of setup that's required to even get to a point where you can read something on the screen. This is the initializer for Vulkan. It's the first thing you need to do. Well, obviously the first thing you need to do is include Vulkan. GLFW is here so that I can create a window without having to interface with Win32. I don't want to do that. But yeah, so you initialize Vulkan, you need to create an instance of it, which has its own, thing. Everything is passed around through these structs that Vulkan has. That's how it handles all of its information. Then you just set up a debug messenger, otherwise you don't have any debugging information because Vulkan disregards that in favor of performance. You need to create a surface to render to. You need to pick a physical device, which that's like your actual physical GPU graphics card, and you need to find something that has correct support. So this like enumerates the actual physical devices in your system, and then decides if it's suitable based on its extension support, what it actually, what the device reports when you query it. It also checks for swap chain support. Then you need to create a logical device with which to interface with the GPU physical device that you've created, which has its own set of information structures. And then you need to create a swap chain so that you have something to render to, which is a very involved process. You need to create image views within the swap chain. You need to create render passes. You need to define what a render pass is, basically. And then all of this goes together within the graphics pipeline. And for the graphics pipeline, you need to create shader modules so that it knows what shaders to use, which means that you need to define your own shaders. I don't know why that happens. I don't know why it won't let me open it. It's literally just a text file. Oh, maybe those are different pointers or something. I don't know. They're right here. There it is. That's it. Very simple fragment shader. And then here we have hard-coded vertices to draw the triangle. And then the fragment shader contains the colors. So you see this. They're written in GLSL and then compiled with this little program into Spur 5 or Spurv. I don't know how to pronounce it. SPIR -V. Compiled using that into those, which is the only format that Vulkan understands. You can't use these natively. So yeah, you create your fragment fragment shader and your vertex shader modules, and you can see them being read in here, which that was another function I had to create, right? Reading in the actual thing because it's a bytecode file format. So once you have that, you got to come up with a struct to specify all the info for the vertex shader stage, and then you do the same thing for the fragment shader stage. This defines how to receive vertex input. This is the input assembly, and then down here we have like viewports, which is like a part of the screen that you're rendering to. It's just the full screen right now. That's it. but I could change it to like a small part, like the top left corner, and then divide it into subdivisions and create like split screen. A scissor is if you want to like crop part of your image, basically. Very basic. Viewport state is part of the actual pipeline, just like the vertex input state. Each piece of the pipeline is a state. This is the actual rasterizer. Of course, you need to create a struct info for it and fill all that out. And then here's the actual. This is for multi-sampling. I'm not actually using multi-sampling, but you need to define something. This is for depths and stencils. That's not being used. Down here is for color blending. That's not really being used either. This is just a bunch of superfluous information for myself in the future. This is for blend states. It's the same thing. I'm not really using it, but you need to define something. And then here's the layout. Create info for the pipeline. We still haven't created the pipeline yet. We're still preparing to create the pipeline. And now we're creating the info struct for the pipeline. This is the layout for the pipeline and what order things go in. And then finally down here we can create the pipeline. And if it fails, we throw a runtime error. And then we don't need our shader modules anymore, so they get destroyed. But they get like physically linked to through the linker through these functions. And that's how you create a pipeline, which is its whole enormous, gigantic function. Probably the biggest function I've ever written. Let's go back to the init. Here we are. So once you create your graphics pipeline, you need frame buffers to render frames to. You need a command pool to execute commands, because that's how Vulkan works. Vulkan takes commands and puts them into a command pool, and then you execute. It pulls off the top of the command pool and then executes commands. The command buffer to put commands into so that they can be assigned to the command queue or pool. I'm sorry. And then you need sync objects, because everything in the actual draw frame function, all of this is asynchronous, and they don't really tell you that, and so you need to synchronize things with like mutexes, but Vulkan calls them semaphores. It also has this thing called fences, which is a different thing. It syncs a bit differently with regards to threads. There's instances where you need to recreate the swap chain if you resize the window, right? Because then your frame buffer is invalid. So if I go like this, the frame buffer is invalid, and you have to recreate the entire swap chain, because you can't dynamically create parts of the swap chain. You have to create the whole thing at once. So that's what this is. Yeah, so that's a very, 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 very brief, basic overview of how this works. The main loop literally just checks if the window should be closed or not if I click the close button, and if I don't, it will continue to pull events, and then it will draw the frame forever. And then once this is done, we need to wait so that we don't start cleaning up resources while I'm closing, while stuff is still like being drawn, because you can exit this while this is still executing, since it's asynchronous, right? So without this, you could start deleting things. Like, watch, if I remove it, it's probably going to give me a bunch of errors when I hit the close button. Yeah, see, poops out a bunch of garbage. It's like, oh, you can't do that because you're deleting things when they're trying to be used, because we didn't wait for it to finish first. So that's what that's for. This is just a cleanup function to destroy any memory so that we don't have any leaks. And then we're into all the actual functions. And if you go down here to the main, at the bottom of the program, we have the entire application contained within its own class. Hopefully in the future I want to try to separate everything into header files and CPP files to make the code a lot more easier to manage, because this is just absolutely horrible. I would have done it as I went, but I had to get this done in a week, so here we are. So yeah, it's just contained in a try catch block. It goes into the run, which inits the window, and it's Vulkan, and then goes into the main loop and then cleanup. That's it. catches an exception. If anything is thrown during this, it will print it out to the C error standard out stream. I don't know what you call it. Prints out whatever it was and then ends the line. Pauses, which is a macro that I defined, and then returns exit failure if it caught something. Pauses and then returns exit success if it didn't. Exit success is just a macro for 0. Exit failure is a macro for 1. Those are defined all the way up here. There's my pause, and then one of these, I believe it's C standard library, gives you the macros for exit success and exit failure, just so that it's easier to read. And this is for like debugging. You have to actually assign a callback for the debug messenger. This is what actually prints the information into the console. I put validation layer because, and the guy that was explaining it was like, just had it like this without this, and it doesn't tell you what validation layer it came from. Validation layers are unique to Vulkan. You can choose to run them or not. So if I run the program in this checks for debug mode. So if I switch to release mode, we don't have any validation layers, and the program runs a lot faster because we're not trying to debug anything. It's missing some input up here, and you notice it's using significantly less memory over here, 44 instead of like 81 or whatever it was before. But that's one super crazy good benefit, is you don't have to have debugging at all if you're in release mode. I also don't like having a lot of these global values. Hopefully I can put them in like a class that's like called global or something, and then make that public, or figure it out. I don't know. But yeah. So I'm sorry it's not something crazier and more useful or more demonstrative or something. But this took a lot of work. And I'm pretty proud of it. And hopefully I can iterate on it in the future and turn it into a full Minecraft clone next month. But from here on out, it shouldn't be that much more effort to start rendering fully 3D objects. So yeah, thanks for watching.